now what we have done approximate methods how to calculate whatever energies and so on. Clear? We have done the variation approximation. Okay, so these are the approximate methods what we have done. Okay, then we have done scattering theory. Clear? Got it? So we have done the Green's function in the last lecture. Now we'll be taking the identical particles. Okay? So we'll be considering now two or more than two particles, how to deal with that. But before doing that, we'll recap what we have done for a second half particle. Clear? You have already done the angular momentum, but let's do the some algebra. Let's repeat that algebra for spin half. Okay? So then we will consider the journal. So we'll consider only one particle that carries spin half. So the effective Hilbert space here is two-dimensional Hilbert space. Clear? Got it? Okay. So if you are having angular momentum, let's say, so you are having angular momentum operators. So let me repeat it here. So you are having angular momentum operator defined by some J. This is a total angular momentum operator. Clear? So the J, these are also known as the generators of the rotation. Let's say if you want, okay, so let's put it this way. So you want to rotate a vector, let's say in 3 dimensions. Or you are having a vector that is defined, that represents some quantum state. And you want to rotate that vector. Clear? So an operator that we call an angular momentum operator J, it acts as a generator for the rotations. The way you are having momentum as a generator for translations, similarly the angular momentum operator acts as a generator for rotations. Okay, so these J satisfy this kind of commutation. We call it as a Lie algebra, a closed Lie algebra. Clear? So it is known as Lie algebra. Okay. So now if I take, let's say if I am taking J is equal to half, then the operator, okay, so for that we'll write that as S. So we'll write the spin of the, okay, so angular momentum operator as S. So where SI, SJ, those are equal to I, the same thing, IH cross. Clear? And there is a sum over K, huh? Okay. So there is a sum over this K, and there is a sum over this K, and what is IJK? IJ equal to 1, 2, 3, and similarly for the other case. Clear? So much, yes, so instead of taking now, okay, if I am taking J equal to half, I will define now my rotation operator to be what? S. Clear? Okay. Now, so the components of this S, I can write now, let's write this SX operator. Okay. Got? Okay, so let me write this S as how many components? 3 components. Sx, Sy, and Sz. The same way you are having here Jx, Jy, Jz. It is the same angular momentum what you are doing. Now let's try to figure out what is the matrix representation of this Sx, what is the matrix representation of this Sy, and what is the matrix representation of Sz. Clear? Okay, so what I will do, okay, so the matrix representation is like this thing. So I can write this Sx as, for spin half particle, H cross by 2, 0, 1, 1, 0. Okay? And Sy I can write as, anybody give me an idea how to write it? How to calculate these matrix elements? One, 0, 0, minus. Clear? So these are the matrix representation of these S operators for what? Okay? For this Sx, Sy, for spin half particle. Can anybody give me an idea how to calculate these matrices? You have done it. Okay, so I will give you an idea. So you are having, okay, J square acting on Jm, that's equal to H cross square J into J plus 1 Jm. Clear? then you are having this jz. So you choose a basis. Okay, you choose the eigenstates of jz, because j square and jz commute. So what is that? M h cross j m. Clear? So then you, okay, so I will give you the hint. I will not calculate directly. Then you define a raising operator j plus. So it is jm. So that will be a constant. Okay. So can anyone give me what is the value of that? So it is j minus m into j plus m minus 1 probably. Yeah? So just check it. So it is what? J into m plus 1. Similarly, you are having now what is j minus j m acting on like this thing. So it is j plus m into j minus m plus 1. Okay? J m minus 1. Okay. So I am giving you the prescription how to calculate this sx, sy and sz. Now what is our j here? Now tell me. So our j is half. Clear? So what are the values of m? M is equal to plus minus half. Got it? So what you will be calculating? J plus acting on half, okay, and minus half. There will be two states. Clear? So you have to calculate it on these two states, half and half minus half. Okay? So now let me calculate then. If I take jx, so that will be simply j plus j minus divided by 2. And jy I can calculate as what? J plus minus j minus divided by 2i. Because how you have defined j plus? If you remember, j plus minus is actually equal to jx plus minus I jy. Okay, so you know j plus j minus. Okay, j plus acting on this thing. You take now the matrix elements. Okay, so you take, let's say, the matrix elements of this thing. Let's say half and half, all the possible matrix elements, you will be able to figure out the matrices. So this is how we define the matrix representation of these spin operators. Similarly, you can go for matrix representation for, let's say, spin 1. Let's say if you are having j equal to 1, how many m values are there? 3 values. So you can be able to construct the spin matrices corresponding to spin 1. Similarly, if you are having spin s is equal to 3 by 2, you will be able to calculate all the matrices corresponding to spin 3 by 2. Clear? And so on. Got it? Everybody followed it? So this is already you have done. I have given you the idea where from I can calculate these matrices. Okay? So okay. So let's take, okay, so let's call eigenstate, okay, so let's take sz. Since in that representation I am taking jz to be diagonal. Now look here, which matrix is diagonal here? Sz. Is sz diagonal? Okay, so I am taking, let's take eigenstates of sz. Okay, got it? So what are the eigenstates? It is, okay, so let me write those as, let me write one of the eigenstate this way, 1 0, and another eigenstate minus, okay, like this thing. This means, okay, so you are having spin, so let me write it this way. Okay, so let's say, what does it mean? It means your spin is oriented either along the plus z direction or along the minus z direction. Clear? So when I am okay, so what does it mean? So if I take now sz acting on this plus, what you get? So h cross by 2, 1 0 0 minus 1 and 1 0, what you will get? So simply h cross by 2 plus. So if you take minus, so you will get plus minus. So that means, so this is the this state is having an eigenvalue of plus h cross by 2. This is having what? Minus h cross by 2. Clear? So now what is our basis? It's a two-dimensional basis. Described by what? Spin oriented along z direction or spin oriented along minus z direction. Clear? Everybody followed it? Or there is any problem? Okay? So it is actually the continuation what we have been doing for the vector algebra. Clear? So Dirac bracket and notation. So I'll be heavily using that notation here. Okay? Okay. So now let's take, okay. So one more point. So if you take now plus plus, so this will be 1. If you take minus minus, that is equal to 1. So plus minus, that is equal to 0. Got it? So it means these two states are orthogonal. So in other words, plus and minus, they are the linearly independent states. Got it? Okay. So now let's check the completeness condition. Okay. So let's check the completeness condition. So if I take now plus, it is like this thing. That means you have to take the output product of the states plus like this thing, minus minus, that is equal to. Now let's check it. Okay, so let's check it. What is plus plus? Okay, so let's check this thing. Yes? Yes? Huh? So if you remember, what was the, okay, so we considered a vector alpha, then we considered a completeness condition, is it? So in a given basis, you remember it? So we have like this thing, summation of n alpha, clear? And you have here what? Summation of n, and what this should be equal to? N identity matrix or an identity, clear? Now let's check this thing. So what this object is? Plus? Plus is what? 1 0. What this is? 0. Okay, 1 0. So it is a column vector, it will be a row vector. Then you are having 0 1 and it is 0 1. So if you calculate, what you get? 1 0 0 1. What is that? Identity matrix. So what is your completeness condition then? So this okay, here you are having an n-dimensional space. So you take the sum of all these kinds of objects, they should add up to a unit matrix. Clear? Here how many vectors you are having? Two vectors. Take these two states, I mean these two objects, and check whether their sum is equal to unity or not. Okay, so you have got an identity matrix. Clear? Samajh? Okay. Any question? Okay. So now, if you are having a basis, okay, so let me tell. Okay, so let me first write the vector, then I will repeat it what I am doing. So I will take now an arbitrary vector that represents the state of a spin half particle. Clear? Samajh? You are having a spin half particle. Let's describe that by some state vector what? Alpha. Clear? So I can express it in terms of the basis. Can I express this? Okay, so what I have to do? Like that. So that means I have to introduce an identity like this thing. So you write an identity here. Okay? Like this thing. The way we have done here. So what you have? So it is alpha plus minus alpha. Got it? So now this is an inner product between plus and alpha, and this is between minus and alpha. Clear? So these are complex numbers in general. Let's call this as C plus, call this as C minus. So this is actually your representation in the two-dimensional space. So you can express your state of a system as a linear combination of up and down spin states. Got it? Okay, so let's recap what we have done. Okay, so we have constructed a spin half particle. Clear? And for that, we have constructed the components of the spin vector or the spin operator. It is Sx component, is Y component, Sz component. Clear? So what we have chosen? We have chosen Sz to be diagonal. Clear? Because the representation what we have started with, in that Z component of the angular momentum is diagonal. Clear? If you see, it is actually a diagonal. So if, okay, so let me write, if you are not able to understand it, so let me write J prime M prime, Jz, Jm. So J is fixed. So it will be simply M H cross. So Jm prime, Jm. Clear? So what this is? So it is MH cross delta MM prime. Got it? Now is this a diagonal? So that means you have chosen a representation in which Jz is diagonal. So when you are choosing one component to be diagonal, you have figured out the other components, other matrices Sx and Sy, and they will turn out to be the off-diagonal objects. Clear? Now what is at hand? So our representation is such that my spin is oriented only along what? Z direction. That means either along plus direction or minus direction. Both degrees of freedom are independent, or both represent degrees of freedom. Clear? 2 degrees of freedom. It means you are having a two-dimensional Hilbert space. Got it? Now I need to figure out what is the basis. Okay, a basis set that will describe the Hilbert space. So a suitable choice is that take the eigenstates of Sz. Got it? So I have chosen the eigenstates of Sz. They are orthonormal to each other. Clear? Samajhan? And I have expanded an arbitrary vector. This arbitrary vector actually describes the state of a spin half particle. Samajhan? Okay, so that I have written in terms of the spin up and spin down states. Okay, so now let's consider, let's say you are having an electron. Clear? Forget about its special components of the wave function. So you have only what? It is spin degree of freedom. Clear? How you write it? You write it as actually the linear superposition of up and down spin states. Okay, so that's exactly this. Samajh? Okay, so this is one choice why I have chosen Sz to be diagonal. You can say let me choose my spin oriented along plus x direction and minus x direction. Clear? You can equally choose that representation. In that case, Sx will be diagonal, but Sy and Sz will be off diagonal. Clear? And the basis what you choose, that will be represented by the eigenstates of Sx. Clear? समझ आया? Okay, good. Because I know now the eigenvectors correctly. Eigenvectors linearly independent है ना? Look here. The important point is here Sx, Sy, Sz, they do not commute with each other. Is it? So that means you cannot describe them simultaneously. So how you have to do? Now, in order to construct an angular momentum basis, you need to construct, let's say, the state space. Okay? So what you need to for that? You need to construct the independent set of independent vectors. Where from that comes? That comes from you choose actually this j square, or in other words s square. Okay, that commutes with this sz. J square commutes with jz, or j square commutes with sx. J square. Okay. So j square commutes with jz. J square commutes with jx. J square commutes with jy. So these are three commutation relations. Now you have to figure out which you will take as your representation. Clear? So you can equally choose, let's say, j square and jx. Okay? So you cannot choose them simultaneously. Why? The reason being jx, jy, jz, they do not commute with each other. You cannot measure them simultaneously. Okay? So you measure simultaneously j square and jz, or j square jx, or j square jy. Clear? Got it? Samajh? Okay. So now let's write these. In this representation, this sx, sy. Okay. So let's write this sx. So Sx, can I write this h trans by 2? So now look here. So let me put it in terms of the vectors. Huh? Okay. So this thing. So I can write it as plus, minus. So this plus means your spin is along where? Z direction. Huh? Okay. So I am not putting as z explicitly here. I will write it like this. Can you check it? So I can write it in this way. Yeah? So in terms of the outer product of plus and minus, minus and plus. Got it? So it is simply as a shortcut notation to that matrix. Eh? So I'll be often using this kind of notation instead of the matrix. Okay? So you can check it. Okay, so what this is? So let's check it. What this object is? It is 1, 0. So what this is? It is 0, 1. Like this thing. Yeah? Okay? Then what this is? It is 0, 1, and what this is? 1, 0. Clear? So let's calculate this objective. So it is 0, 1, 0, 0 plus 0 0 1 0. So what that is? 0 0, sorry, 0 1. Okay, clear? Got it? Okay, similarly, I am having this sy as h cross by 2. Okay, so what y is having? It is having minus I and I. Clear? Got it? So I will put it as minus I plus minus plus I minus. So you can check it. So this minus will come here. Yes. Okay. So now let's write sz. So sz is what? H cross by 2. What that will be? That is the diagonal terms. So plus plus. That will give 1 0. Then you are having minus minus. Clear? So now from here it is easier to check the commutations. So you can check the commutations. Okay. So let's say sx. Okay. So let's take sx sy commutation. Okay. So let me write it. So what is sx and sy? So you are having this as a matrix representation. So it is sx sy minus sy sx. Okay. So what it is? H cross by 2, h cross by 2. So what that is? H cross square by 4. So now let's write. So you have to take sx acting on sy. So what that is? So it means, okay, so take a look. So this object acting on this thing. You are having minus here, then you are having plus here. That will give you 0. You are having this minus here, this minus. It will give you 1. Clear? So what you are having? Plus and plus, but with an I. So you are having plus, plus. Clear? Okay. So now let's take a look at this thing. You are having, okay. So we are taking this term first. So you are having now plus here, then you are having plus here. It will give you 1. So it is minus I minus minus. Now look here, you are having plus and minus, that is equal to 0. It comes from the first term. Now let's take the second term, h cross square by 4. So what is sy? So this one. So you are having minus plus. Clear? So this minus will act on this plus. It is an overlap. Okay, so that is 0. This minus and minus, that is 1. What you will get? Minus I plus plus. Then you are having this term will contribute plus and plus. Okay. So I minus. Clear? Everybody followed it? Huh? So it is simple. Huh? Okay. So now if you check it, it will be. Can anyone tell me what it will be? I can write it like this thing. Anybody? Okay. So anybody? So it will be I times h cross by 2. Okay. Plus minus minus. Clear? So what is that equal to? I h cross. So it is h cross square. I'm sorry. H cross. Then you are saying sz is actually what? H cross times this thing by 2. Clear? So you have got now the commutation. Similarly, you can do all other commutations. Clear? Yes, any question? Okay. So now we can do something different. So let's consider. Okay, so you have written it? Okay, so let's consider rotation. Huh? Okay. So now let's try to rotate my vector. Any question? So how to do it? I have to apply a rotation matrix. Clear? Or I have to apply a rotation operator. How you have done it? So let's say if you are having some state vector. So now take a state vector, arbitrary state vector alpha. You want to rotate it through an angle theta or through an angle phi. Clear? Along an arbitrary direction. Okay. So rotate this vector through an angle phi, okay, in arbitrary direction, in the direction n, where n is a unit vector, okay, describing your direction of the rotation. Clear? So how we describe it? So you describe it like this thing. So let me take the rotated cat. So you write it, you apply some operator. Clear? So let me call that operator as d. So it gives you, okay, so let me write it as n phi. Clear? So you apply an operator, okay, on a state alpha. So it rotates, this operator rotates this alpha through an angle phi in an arbitrary direction n. So let's say if n is your z, clear? Let's say n is equal to z. That means this operator will rotate your vector in z, about z direction. Clear? So that means there will be a rotation in xy plane. Clear? So how to specify it? So this rotation operator is given by like this thing, e raised power minus I j dot n phi by h. Okay? So have you done it somewhere? So this is how we define. Okay, look here. So this is actually a matrix. Okay, so when you consider, this will be a matrix. Okay, so this matrix will be constructed from your total angular momentum operator j. That is what I was saying. J represents the generator for the rotationals. Clear? So remember this formula. Okay? No, it's not a phase. You will see it is not a phase. Okay? It's really not a phase. It is simply a rotation through which angle? Through a rotation through an angle phi. And J is the angular momentum operator. We call it as a generator, which describes your rotation. I hope this you should have done in your previous code. No, not neither. Simple rotations. Then what we have done in the rotations. Okay, so let me give an example this way. Okay, so let me describe an analogy instead of deriving it directly. So let's say you are having some state vector, position state vector x. So let's describe it. So you should know these things. Okay. Okay. So let me take a position vector x. Clear? So now apply some translation operator on it. Clear? So what it will give me? So let's say you are having a translation to an infinitesimal amount. So what it will give you? X plus dx. Clear? So now you can expand this thing. Okay, so instead of, let me write it in terms of the wave function, that will be very much clear. So let's write a translational operator acting on this thing. What you will get? Psi of, let's say through an infinitesimal amount a. So it will be x plus a. So now let's write it. So let's expand it. So it is psi of x plus a gradient of psi of x plus so on. Clear? So can you write it as 1 plus a gradient plus so on, all these things? Okay. So what you will get? So you will get an operator exponential of, okay, a gradient psi of x. So what you will get actually e raised power minus I p through an, actually I should put it, since this is an infinitesimal amount, so let me write p dx through some p x by h cross psi of x. Clear? Yes. So okay. So x is actually the finite value of epsilon. Okay, so you put an infinitesimal amount here. So then write the finite amount. Okay, so this will be some finite amount. So let's write some a, yeah? A dot lambda. So it will be actually of this form. E raised power minus I p dot x by h cross. So let me take this thing. So it means this. Oh, okay. So what you have here? So you are having an operator p. Okay. So which translates your wave function through certain x. Clear? Or in other words, it translates your wave function through a finite distance of a. So much, Shaman? So what does that mean? So this I call this p as the generator of the translations. Okay. So now if you okay, so let me put it this way. Now if you consider a translation, let's say in along x direction, then translation along y direction, and come back. Got it? So are they same? So if you consider, let's say, translation along x direction, then translation along y direction, then do like this thing. Translation along y direction, then translation along x direction. This means translation along x direction, then y, then you are hanging along y, then x. So do they commute? So they are the same things. Suppose you move this way some steps, then move by some steps this way, and return back, you will reach to the same point. Clear? So that means there is no difference between the two. It means they will commute. Clear? So it means the translational operators, they will commute with each other. What does that mean? So that means you are having a generator along x direction, generator along y direction, and generator along x direction, generator along y direction, x direction. This should be equal to 0. So now you see px py commutes. Clear? Got it? So similarly, now let's consider the rotation. So here it was an operator that describes simply the translation. Now let's consider the infinitesimal rotation in the xy plane. Clear? How you describe that? So let's say you are having an operator t that describes the rotation. Okay, so this operator describes the rotation, infinitesimal rotations. What does that mean? So now you need, okay, so let's take x, y, z. I will take these three coordinates explicitly. Clear? Let's say the rotation is along which direction? Z direction. Clear? So that means you are rotating in the xy plane. Okay, so what it means? So x will go as, okay, tell me, it will go x cosine of theta. Let me write here first the transformation, and it will be minus x sine theta plus y cosine of theta. Z will remain as such. Since I am considering the infinitesimal one, so cos theta will be 1, so it will be simply theta y, and here it will be minus theta x plus y, and then you are having z. Clear? So now you expand it. So just expand it about which x, y, z. Then what you will be having? Now tell me, theta partial by partial. So what you will be having? So you will be having theta y partial by partial x, then minus theta x partial by partial y psi plus dash dash. Clear? So it is the infinitesimal one. Got it? So now if you see what this operator is, so it is simply your Lz, theta times Lz operator. Is it? So with an I sign, obviously it will be minus I by h cross here. So let's forget that, but it will be actually what? Z component of the angular momentum. That means it generates, this Z component generates your rotation about Z axis or in the xy plane. Clear? So along the same arc bands you can now consider. So now you can exponentiate it the way we have exponentiated this thing. Clear? You can put it in the exponential. Now what you will be having in the exponential? So it will be simply e raised to power minus I Lz to an angle, let's say theta by h cross. Clear? So that means this operator will represent your rotation about, and okay, in xy plane or about z axis to an angle theta. Clear? So now since, okay, if I consider now a general rotation, what that will be, how that will be described by? If you consider a rotation, an arbitrary rotation in 3D plane, clear? So what you have to do? That means you have to invoke all jx, jy and jz, clear? Or in other words, all lx, ly and lz, clear? So that what I have done here. I have introduced a total angular momentum operator that makes an arbitrary rotation through an angle phi in the direction of n. Clear? Got it? Now you, okay, so that's why we call this J as a generator. So, now these generators satisfy what I have already told you. They satisfy this kind of relation. IH trans epsilon IJK JK. Clear? So in other words, these matrices in general will not commute with each other, because J's do not commute with each other implies what? This we call this as a rotation matrix. Okay? So this rotation matrix, you know the rotation matrices in general do not commute with each other. Let's say you take a rotation along, so let's say about z axis, then rotation about y axis. Clear? So and you move along. Okay, so consider the reverse rotation, you will not reach to the same point. Clear? Samajh? Got it? Everybody? Okay. Okay. So now let's consider. Okay. So let's take about. Okay. So now tell me what is about the z-axis. So therefore D along z-axis. So through an angle phi. So how it will be J. So it will be simply JZ phi by H. Clear? Samajh aa? Similarly, you can put along x-axis, y-axis, and so on. Clear? Okay. So now let's consider the rotation of this these spin half particles. This is for the general case. So let's consider spin half. Okay. Samajh aa? So let's describe. Okay. So let alpha represent state vector for a spin of a spin half particle. So alpha is some state vector of a spin half particle. That means you can consider it as a linear superposition of both up and down states. Clear? It can be either up, it can be down, or it can be along x direction, or it can be along y direction, whatsoever. Clear? So this is an arbitrary state corresponding to a spin half. That there I have written as a general case. Clear? So now tell me under rotation. Now tell me what will happen. So under rotation, this alpha will get rotated. Clear? Samajh aa? So that I have put as script word R here. R means it's a rotated cat. So how I induce the rotation now? So E. Okay. So let me write. Okay. So let's write E raised power minus I. Now instead of J, what it will be? Because I am rotating in the two-dimensional space. Clear? Okay. So what it will be? S dot N by H cross acting on alpha. Because here our angular momentum is what? Spin angular momentum, not the total angular momentum. Clear? Okay. So if I consider now, okay, so about z-axis, so let's consider the rotation about z-axis. So what does that mean? So this alpha will go as alpha rotated. So I'll put it as simply E raised power minus I S Z phi by H cross acting on alpha. Let's write that as dz phi, okay, acting on alpha. Clear? So I am taking dz of phi is what? This object. Clear? Everybody? Yes. Okay. Okay. So now let's calculate. Okay. So let's calculate the components of this. Since this alpha, okay, it's a vector. Clear? How many directions are there? Think in terms of the directions. How many directions are there? 3 directions. Along x direction, that means spin oriented along x direction, or y direction, or z direction. Clear? So that means I can express this. I can have 3 components of alpha. I can evaluate, let's say, for a spin half particle, the average value of s in alpha, in the state alpha. Clear? So what I mean by that? Okay, so let me write. So let's calculate this thing. So let's say you are having alpha and sx. Clear? So let's calculate the. That means I am getting the average value of sx. Clear? So instead of calculating this thing, what I will do, I will just look at how it rotates. Okay, what is the effect of rotation on this average value? Is this an average value? Clear? Now let's check how this average value behaves under rotation. Clear? So it means, okay, so under rotation. So let me take under rotation around z-axis. Okay. So how it goes? So it will be like this thing, alpha. So a rotated cat, because now alpha will get rotated, clear? And then you are having sx, so alpha will be rotated, clear? Okay? Everybody? Okay. So what is that equal to? Now tell me. So what is this alpha? Alpha rotated is dz. Okay. So it is dz through phi and alpha unrotated. Clear? Got it? Now then you are having sx. Okay, so this object is actually the conjugate of this thing. Okay, so I will write it as something alpha, then dz dagger phi. Clear? Everybody? Okay, so what I need to calculate then? So I need to calculate this object. Okay, so the state vector is at hand. I know it because I stated with a state vector alpha. Clear? Got it? What is now unknown to us? I mean, what we need to calculate? This object. Clear? Samajh? Okay, so let's call this as first. So now there are two ways to calculate this very object. Okay, so I will use both ways to show you the power of this algebra. Clear? Okay. So let's say, okay, so there are two ways to evaluate. Okay, so I will tell you reason why there arise two ways to evaluate this. Okay. So first thing, okay, so let's write first use. So you are having dz dagger phi, okay, sx dz phi, clear? Okay. So let's write in the first. What is the form of sx in the representation? No, sx. So let's write first a d dagger. Let's write d dagger. So it's e raised for I sz phi by h cross. Because sz is what? Hermitian. Sz dagger is what? Sz. Okay, minus I dagger is plus I. So what is this sx? It is actually h cross by 2 plus minus plus, okay, minus plus. Clear? Then you are having e raised for minus I sz phi by h cross. Okay. So now why this method works, this kind of method? The reason being this plus is actually an eigenstate of sz and minus is also in what? Eigenstate of sz. Clear? So let's say if it is an sx here, then this method will not work because this is not an eigenstate of what? Sx. Clear? So the reason being, so this is an operator. Now it will act on this plus. So it means if this is an eigenstate of operator here, so it will just pick up the value, the eigenvalue. Clear? Oh, samajh? Okay. So this h cross by 2 I will write outside. Now tell me. So e raised for it sz will act on plus. Clear? So what that will give me? H cross by 2. So samajh? So it is e raised for I phi by h cross. Then you are having h cross by 2. So now operator is gone. Clear? So samajh? So h cross by 2 is actually the value for what? So I'll be using sz plus minus is equal to plus minus h cross by 2 plus minus. Clear? Okay. So now you are having this sz. It is coming from the back side. Clear? It's a Hermitian matrix. It's a Hermitian operator. It will act on minus. Clear? So what that will give me? E raised for minus I phi by h cross. What is sz acting on minus? Minus h cross by. Clear? So now on this thing, e raised for this thing, sz will act. So it is e raised for I phi by h cross. Sz will give me minus h cross by 2. So you are having minus plus. Here it will give you minus phi by h cross by 2. Anybody having confusion here? Just tell me, I can repeat it. Everybody? Okay. Okay. So now let's write it. So it implies this d dagger z phi, okay, sx dz phi, okay. So that's equal to h cross by 2. So it is e raised for This is e raised for I phi by 2, another is e raised for I phi by 2. It will be simply e raised for I phi. Clear? Yes. So plus minus e raised for minus I phi minus. Got it? समझ आया? So now let's write it e raised for in terms of cosines. Okay? So because it does not look nice, is it? What you are having here? Sx operator. And I don't know what this object is and what the other object is. Clear? समझ आया? So let's write it in terms of this thing. So it is cosine of phi plus I sine of phi. Okay? Plus minus. Okay? Cosine of phi minus I sine of phi, then you are having minus plus. Clear? So take in the first term cosine out, cosine of phi what remains inside, plus minus plus minus plus. Clear? So the other term is minus I sine of phi. So let me write plus sine of phi. Okay, I. So let me write I inside. So it is I plus minus. Okay, so I will take minus out, put a minus here, so it will be plus I minus. Let's just readjusting the minuses. So, समझ आया? Now, can you tell me h cross by 2, this object is sx, clear? And h cross by 2, this object is sy. So, it is actually equal to cosine of phi sx minus sine of phi, what? Sy. So, what you got therefore? So which implies the rotated state. So this alpha sx alpha. So under rotations about zx is what you get. So it is actually the this thing. So it will be simply sx minus sine of phi sy. Clear? So let's plug in the equation 1 there. Eh? समझ आया? Okay. So what I am saying, okay, so we need to evaluate this object, clear? So let me put it in, okay, this way. Okay, so I know this plus and minus are eigenstates of Sz, clear? So it makes actually it gives us two possibilities to evaluate this product, clear? So this is actually essentially a product, clear? Product between the operators. Okay, so let's take this operator and I am having this thing. Now I know, okay, so this Sz will act on plus, it will give me h cross by 2, clear? Now, if it would have been, let's say, Sx, then this, I don't know how it will act on it, because this is not the eigenstate of what? This operator, clear? समझ आया? So, for that matter, okay, so this is an eigenstate, it makes my work simpler. So, it will give me simply e raised for I phi by h cross, as that will act on this thing, it will give me h cross by 2, clear? Now, you are having an operator acting on this side as well, because you are having this set, this cat and this brass state, clear? So you are having e raised for minus I by h cross, as that will act on minus, you will get minus h cross by 2. Similarly for the other term, clear? Got it? Now when I simplified it, it turns out to be this thing. Okay? So now I have put it in terms of cosine and sines. Got it? So what you are having? Cosine of this thing, and you identify this as sx and you identify this as sy. So now let's substitute it back where? Substitute in second. Call this second instead of 1, because 1 we have written some. Okay?
Rotation matrix. Rotation matrix में दिया था ना cos pi sin pi 0 0. Rotation matrix.
नहीं. Wait. I got your point. Wait. So let me finish it, then I will tell you. Okay? So is it now clear? So when you substitute it in second, what you have to do it? So that means the rotated state is this thing. Clear? So समझ आया? So it means if you are rotating, so it means this average value under rotation gives you what? At the computation of average of Sx and Sy. Got it? So similarly, now let's calculate. Let's do the other way. So if you calculate, that I will keep as an assignment. So take alpha Sy alpha and alpha Sz. Okay. So you have to go along the same line. Clear? I will do the second method. That will be very helpful. Clear? Okay. So let's take the second method. Clear? So okay. So I will write then. Let me do the second. Huh? Okay. So let's stop here.